issue here. Yeah. Okay, I'm going to show you another way to create groups. That's with the command generate by relation. This function has two lists as input. First list contains the generators, and second the relations. The most simple group I can think of is the cyclic group of two elements. KD table. Okay, that's this is the cyclic group of two elements. So if I would change the 2 to a 5, for instance, then I would get the cyclic group of 5 elements, of course. In this format you can only create cyclic groups. But if I would add another generator, say B, and add some relations as well, like for instance A to the third is E, B times B equals E, and A times B equals B times A times A. And if you're familiar with this, you immediately see that this is the group of the triangle. 6 elements. You can look at the group properties. It's not an abelian group. It is not cyclic. Exponent is 6, I think. It has a center. No, it has a. No, it's 1. Yeah. Okay. Another one maybe. The abstract form of the quaternion group may be interesting. We have A to the 4th power is 1. And then you have B to the 4th power equals E. And you also have A squared equals B squared. And you have A times B equals B times A third. These are the abstract relations of the quaternion group. If I'm correct, yeah. This is not correct. No. It should be like this. Was that in fact minus 1? Okay, let's test it. It's a group with 8 elements. And if I don't know if it becomes visible in the video, the A is order 4, and the inverse is B squared times A, and B squared is minus 1. So the inverse, if A is I, then the inverse A is minus I. And B could be J. And B to the third is minus J. Or B squared times B minus B. A times B would in that case be K. And so on. This is really the quaternion group. You can also see it on the element orders. So B squared is order 2. E of course is order 1, and all the other elements have order 4. So I minus I, J minus J, so B to the third, and K and minus K, and so on. I could just let this I and J there, but they're also built in Mathematica, so that's might complicate things a bit. But I also want to show you morphisms, homomorphisms in this video. And for that I'm going to make another group. And then I'm going to create a morphism. This function has 3 input parameters, a function, and 2 sets or groups. The function will be very simple. The remainder by division 3. G1, G2, and I could, for instance, the kernel of that morphoid. And if I would make it this, get another kernel, of course. I could visualize the morphoids. Like this. And there's also a way to visualize the kernel. I'm correct, yeah. There are various property checkers on morphoids and so on. But I'm going to keep it like this for this demo. Other features another time.